Some of the biggest breakthroughs in history didn't happen in front of crowds. They happened in silence, in a bath, a basement, or staring at plants for hours. This is a journey through 75 forgotten experiments. Each one small, strange, and secretly world-changing. From invisible forces to boiling frogs, these stories shaped everything, quietly. So get comfortable. You don't need to remember it all. You just need to listen and drift. Let's begin. 1. Mendel's pea plant experiments. Long before DNA and genetic codes became common knowledge, a humble monk named Gregor Mendel quietly worked in the garden of an Austrian monastery. With no fame, no scientific acclaim at the time, Mendel simply tended to pea plants, watching them grow season after season. What he noticed, however, would go on to transform biology forever. Mendel selected pea plants because they had distinct traits. Some bore round seeds, others wrinkled. Some had purple flowers, others white. He carefully bred these plants, crossing one type with another, always recording the results. With each new generation, Mendel began to see a pattern. Traits didn't blend together randomly like many believed, they followed a hidden logic. For example, when he crossed purple-flowered plants with white ones, the first generation had only purple flowers. But in the next generation, the white returned, precisely in a 3-to-1 ratio. He repeated these experiments hundreds of times, always with the same mathematical precision. Eventually, he realized that these traits were controlled by what he called factors, passed down from parent to offspring. Today, we call those factors genes. At the time, Mendel's work was largely ignored. It wasn't until decades after his death that scientists rediscovered his findings and hailed him as the father of modern genetics. What began as a quiet gardening project turned into one of the most important scientific experiments of all time. Quiet, simple, and world-changing. Now let your mind wander, like seeds floating gently on the breeze, and drift off. 2. Tesla's wireless power transmission. Imagine the air around you humming gently with invisible waves of energy. That was Nikola Tesla's dream. In the early 1900s, Tesla was obsessed with the idea that electricity could be transmitted without wires. No more tangled cords or pylons stretching across the land, just clean, effortless energy floating through the air. And he believed he could make it happen. Tesla built a towering structure known as the Wardenclyffe Tower in Shoreham, New York. It rose into the sky like something out of science fiction. Below it, coils, capacitors, and resonant chambers buzzed and sparked. Tesla theorized that by using the Earth itself as a conductor and tuning his coils to the natural frequency of the planet, he could send electrical power wirelessly to any point on Earth. Light bulbs could glow without being plugged in. Ships and factories could draw power from the sky. Though Tesla was able to demonstrate wireless transmission on a small scale, lighting bulbs from a distance and transmitting energy through the ground, he was never able to fully realize the system on a global scale. Funding ran dry, and the Wardenclyffe Tower was eventually dismantled. But his vision didn't fade. Today, wireless charging pads and even long-range wireless power concepts owe their roots to Tesla's experiments. It wasn't just an engineer's dream, it was a whisper of the future. Close your eyes now, and imagine golden arcs of electricity dancing silently across the sky, as you drift softly into rest. 3. Galileo's inclined plane study. In the silence of a candlelit room in 17th century Italy, Galileo Galilei was rolling balls down wooden ramps. It may sound simple, but this quiet experiment changed how we understand motion forever. At the time, most people believed Aristotle's idea that heavier objects fell faster than lighter ones. Galileo had doubts. And so, with methodical care, he began to test his ideas using inclined planes. By rolling balls instead of dropping them, he slowed down gravity's pull enough to measure it. He marked time using water clocks, letting liquid drip into containers as balls rolled down the ramps. What he found was astonishing. The speed of the rolling balls increased in a predictable way, proving that acceleration due to gravity was constant, not dependent on weight. This elegant approach gave birth to one of the first clear applications of the scientific method, Test, measure, repeat. Galileo's findings also laid the groundwork for Newton's later work on motion and gravity. Galileo's inclined planes were more than wood and marbles. They were the beginning of physics as we know it. His experiments helped dethrone centuries of flawed beliefs and replace them with observation and logic. As you lie still now, picture a smooth marble rolling gently down a slope, echoing through time from a stone floor in Florence. Softly, predictably, peacefully, like your breath, slow and steady. Let that motion lull you into a deeper calm, as the weight of the world slowly slides away. 4. Pasteur's Swan neck flask experiment. In a quiet laboratory filled with glass flasks and gently bubbling liquids, Louis Pasteur was on a mission to answer a question that had puzzled scientists for centuries. Where does life come from? Many believed in spontaneous generation, that life could appear from nothing, like maggots in meat or mold on bread. Pasteur thought differently, and he set out to prove it with a beautifully simple experiment. He filled long, curved-neck glass flasks with nutrient-rich broth, then boiled them to kill any existing microbes. The necks of the flasks were shaped like graceful swans' necks, curving gently to prevent dust and microbes from entering while still allowing air inside. Days passed. Weeks passed. The broth remained clear, untouched by life. It was only when he snapped the necks of the flasks or tilted them so that dust could reach the liquid that microbial life began to grow. Pasteur had proven that life does not spontaneously arise. It comes from other life. This idea, known as biogenesis, became the foundation of microbiology and led to everything from vaccines to sterilization techniques. As you listen, imagine the warmth of the softly glowing lab, the glint of glass catching candlelight, and the stillness of the untouched broth. Let your thoughts settle like the dust that never reached those flasks, quiet and undisturbed. 5. Eratosthenes measuring Earth's circumference. Over 2,000 years ago, without satellites or airplanes, a man named Eratosthenes sat beneath the Egyptian sun and calculated the size of the Earth. Not with machines or maps, but with shadows, math, and a little clever thinking. He had heard that in the city of Caens, on the summer solstice, the sun shone directly overhead, no shadow formed beneath a tall stick. But in Alexandria, hundreds of miles north, shadows still appeared at the same moment. Intrigued, Eratosthenes measured the angle of the shadow in Alexandria and found it to be about 7.2 degrees. He realized this angle represented a slice of the Earth's total 360 degrees. If 7.2 degrees was the angle between the two cities, then the distance between them must be about 1/50th of the Earth's full circumference. He measured that distance, in camel days and paces, and multiplied. His result was remarkably close to our modern measurement. No technology, no telescopes, just sun, earth, shadow, and reason. Eratosthenes showed that our planet was round, measurable, and far more knowable than once believed. Now, close your eyes. Imagine standing in a sunlit courtyard, watching a stick cast its perfect shadow on warm stone. The quiet brilliance of an ancient mind still echoes beneath the sky. Let that serenity guide you deeper into rest. 6. Franklin's Kite and Key Lightning Test. One stormy night in 1752, Benjamin Franklin walked into the heart of a thundercloud. With a kite, a metal key, and a silken thread, he sought to catch lightning itself. He wasn't chasing danger, he was chasing knowledge. Franklin believed that lightning and electricity were the same force. To test this, he launched a kite into a brewing thunderstorm, with a metal wire at its top and a key tied to the string below. As the storm rumbled overhead, he stood beneath a shed, holding the silk ribbon to keep himself insulated. Soon, the metal key began to spark. Franklin touched it gently and felt a shock. His theory was proven correct. Lightning was electrical in nature. This risky but groundbreaking experiment changed how we understand storms, power, and the natural world. Though the image of Franklin flying a kite in a storm is often romanticized, the danger was very real. Later attempts by others were fatal. But Franklin's success led to the invention of lightning rods and the birth of electrical science. So now, in the stillness of your room, Picture that lone kite climbing into a darkening sky, its string humming softly with energy. Let the storm remain distant, its power harnessed and understood. You are safe, grounded, and calm, as night falls gently around you. 7. Lavvisers Ice Calorometer. In the quiet corners of 18th century Paris, Antoine Lavoisier was changing the way we understand matter. One of his most fascinating experiments involved ice, chemistry, and the invisible heat of life itself. With the help of Pierre-Simon Laplace, Lavoisier set out to measure how much heat was produced by a living animal, a guinea pig gently breathing in a chamber surrounded by ice. The device was called an ice calorimeter. It looked like a metallic nest of containers, with layers of ice packed around the inner chamber. As the guinea pig respired, it released heat, slowly melting the surrounding ice. By carefully measuring how much ice turned to water, Lavoisier could determine how much heat the animal had generated. This concept was revolutionary, connecting the processes of chemistry with biological life. What made the experiment so elegant was its simplicity. Using only basic materials and logical reasoning, Lavoisier proved that animals consume oxygen and release carbon dioxide and heat, in essence, that respiration is a form of slow combustion. This insight became the foundation for understanding metabolism and how our bodies produce energy. Though the experiment seems gentle and quiet, its implications were enormous. It suggested that the forces driving life were measurable and predictable, tied not to mysticism but to natural laws. In the still of the laboratory, Lavoisier captured the fire within living beings. Now, as you breathe deeply, imagine that warm breath melting away layers of stress, like ice softly turning to water. Let the calm wash over you, cool and serene. 8. Newton's Prism and Light Experiments. In a darkened room with the shutters drawn tight, Isaac Newton made a small hole in the window and let in a narrow beam of sunlight. With a glass prism placed carefully in its path, he watched as that single ray split into a rainbow, casting vibrant colors across the wall. This was no magic trick. It was science. Until Newton's time, many believed that prisms somehow colored the light. But Newton saw something deeper. He realized that white light was not pure. It was a blend of all visible colors, hidden together until something revealed them. By placing a second prism in the path of the rainbow and recombining the colors, he was able to turn them back into white light, proving his theory. This discovery had profound implications. It challenged the long-held belief that white light was a singular entity and showed instead that it was composed of many wavelengths, each representing a different color. Newton's findings laid the foundation for the science of optics, helping future generations understand not only light but the behavior of waves, lenses, and even the nature of color perception. These elegant experiments weren't just about rainbows, they unlocked a fundamental truth about nature. Newton didn't just see colors, he saw order, laws, and structure in what once seemed mystical. Let yourself imagine that quiet room. The beam of sunlight. The glint of glass. The gentle shift of color sliding across the wall. Let the light scatter softly through your thoughts as you drift deeper into calm. 9. Pavlov's classical conditioning with dogs. In a laboratory filled with the quiet hum of curiosity, Ivan Pavlov was feeding dogs. But it wasn't the feeding that made his experiments famous. It was what came before it. Pavlov began to notice that the dogs started to salivate not when they were given food, but when they heard the footsteps of the person who brought it. Intrigued, he designed a series of experiments. He rang a bell just before feeding the dogs, repeating this again and again. Soon, the dogs began to salivate just from the sound of the bell, even when no food followed. The dogs had learned to associate the bell with the meal. It was the beginning of what we now call classical conditioning. This discovery marked a turning point in the study of behavior. It showed that organisms could learn through association, linking neutral stimuli with meaningful ones. Pavlov's work became a cornerstone in psychology, influencing everything from education and advertising to therapy and training. His setup included a harness for the dog, a bell, and a small tube to measure saliva. It was simple yet profound. The experiment revealed how our environment shapes us in ways we often don't notice. Now imagine a soft bell ringing in the distance, echoing through a gentle, sunlit laboratory. You are not being trained or tested, you are simply resting, peacefully. Let the rhythm of calm repetition carry you, like a gentle pattern of breath, steady and soothing as you drift further into sleep. 10. Tindles Dust and Light Beam Study. In a dim, dust-filled room in the 1860s, Irish physicist John Tyndall conducted a series of simple yet enchanting experiments that revealed something profound about the world we see. Using only a beam of light and a sealed glass tube filled with particles, Tyndall showed that light doesn't always travel invisibly, it dances with the air itself. Tyndall passed light through different gases and fine particles to observe how it scattered. When a beam passed through clean air or a vacuum, it seemed invisible. But when dust or smoke was introduced, the light became visible, glowing gently in midair. The reason? The light scattered off the tiny particles, revealing its path. This effect, now called the Tyndall effect, explains why the sky appears blue. Blue light scatters more than red due to its shorter wavelength, which is why we see a brilliant azure dome overhead during the day. His experiments not only helped explain this phenomenon but also laid the groundwork for understanding how light behaves in complex media. Tyndall's work touched more than just physics. His light beam through dust became a symbol for unseen forces made visible, how clarity can emerge from obscurity. In fields ranging from environmental science to optics, his influence still shines. Now imagine a narrow ray of sunlight slipping through your window, cutting across a room filled with quiet dust motes. Each particle suspended like a tiny lantern. Let your thoughts drift in that light, suspended gently, as you slip into stillness. 11. Faraday's magnetic field lines in iron filings. In the early 1800s, Michael Faraday, an English scientist with little formal education but a boundless curiosity, set out to visualize something invisible, the mysterious force of magnetism. In a modest lab, surrounded by simple tools and scattered notes, Faraday laid a sheet of paper over a magnet and sprinkled iron filings atop it. What happened next was almost magical. The filings didn't scatter aimlessly. Instead, they danced into elegant, curved lines that traced the magnetic field, as if revealing a hidden structure long veiled from human sight. This moment, seemingly simple, was revolutionary. Faraday had shown that magnetic forces weren't just abstract ideas or mathematical symbols. They were real, physical, with shape, flow, and structure. The filings mapped the invisible quantities of magnetic energy, radiating from pole to pole in looping arcs. It was the first time people could actually see the shape of a magnetic field. No machines, no sensors, just filings, a magnet, and a spark of genius. Faraday's discovery wasn't just beautiful, it became foundational. His visualizations influenced James Clerk Maxwell, who later formalized electromagnetic theory through equations that underpin modern physics. Yet Faraday, with no formal math training, grasped it through intuition and observation. As you drift into sleep, picture 12. Priestley's bell jar and candle experiment. In the late 18th century, Joseph Priestley conducted a curious experiment that would unlock the secrets of air itself. He placed a burning candle under a glass bell jar, sealing it tightly. As the flame flickered and slowly died out, Priestley realized that something in the air had been consumed. But what exactly? To find out, he added a sprig of mint to the sealed jar and waited. Days later, he lit another candle inside the same jar, and to his surprise, it burned brightly again. Priestley had just uncovered the invisible cycle between animals and plants, revealing how plants release a substance, what we now know as oxygen, that could restore the air. Without knowing it at the time, he had taken the first steps toward understanding photosynthesis and the role of plants in replenishing the atmosphere. This experiment was simple in design but profound in implication. It revealed that air is not a singular substance but a mixture of gases, some of which are essential for life and flame alike. Priestley's careful observations helped shift scientific thought away from vague ideas of phlogiston and toward modern chemistry. As you drift off tonight, imagine the quiet glow of that candle under glass, flickering gently in a world sealed from time. Picture the leaves of mint working silently to cleanse the air, restoring balance with quiet determination. Even in a closed space, nature found a way to breathe. And so can you, one soft breath at a time. 13. Hooke's elasticity tests. Robert Hooke, a 17th-century English polymath, was fascinated by the springs and tensions of the natural world. He devised experiments to explore how materials stretch and compress. Using a variety of weights, he suspended them from coils and wires, meticulously recording how far each material extended under pressure. In time, he formulated what became known as Hooke's law. The extension of a spring is proportional to the force applied to it, provided the material remains within its elastic limit. Though it sounds simple, this discovery reshaped physics. Hooke's law laid the groundwork for understanding elasticity and mechanical equilibrium. It gave engineers a mathematical way to predict how materials behave under stress, whether in the coils of a mattress, the suspension of a bridge, or the springs in your pen. It's a rule that hums quietly through the mechanics of everyday life. Hooke didn't have modern equipment. He worked with brass and string, wood and pulleys. But his precision and patience allowed him to chart invisible forces with startling clarity. He turned the mundane act of stretching a spring into a law of nature. So as you ease into sleep, imagine a gentle spring elongating and rebounding in slow motion. Every stretch, every release, perfectly balanced. Your body, too, relaxes and contracts with each breath, held softly in nature's rhythm. In Hooke's universe, even tension holds grace. 14. Daveys' laughing gas trials. In the early 1800s, young chemist Humphrey Davy began experimenting with a strange gas, nitrous oxide. Colleagues and friends would gather in his laboratory where Davy inhaled the gas and carefully noted its effects. The result? Laughter, euphoria, and a dreamy sense of detachment. This strange phenomenon would later earn it the name laughing gas. But Davy's work wasn't just for amusement. He noticed something extraordinary. Despite feeling lightheaded, he experienced no pain. This led him to suggest that nitrous oxide might be useful in surgery, a radical idea at the time. Though his proposal wasn't adopted immediately, Davy's notes laid the groundwork for the eventual use of nitrous oxide as an anesthetic. Decades later, dentists and doctors embraced it, forever changing the way pain was managed in medical practice. What's remarkable is the way Davy approached his trials, not recklessly, but with curiosity and caution. He documented sensations, physical reactions, even shifts in mood. It was science through self-experimentation, daring and insightful. As sleep washes over you, picture a flickering lamplight in Davy's lab, the faint hiss of gas, and a circle of curious minds sharing laughter in the name of discovery. What began as a moment of levity became a cornerstone of medicine. Sometimes, even joy has a scientific purpose. 15. Boyle's vacuum chamber experiments. In the 17th century, Irish physicist Robert Boyle embarked on a series of experiments that would reveal the hidden nature of air. With a device called an air pump, he created what was then an almost unimaginable environment, a vacuum. Inside a sealed glass chamber, he removed as much air as possible, then placed a variety of objects inside, bells, flames, small animals, and observed what happened. What he found was astonishing. A ringing bell became silent, a candle extinguished itself, and creatures gasped for breath. These weren't just oddities, they were profound clues. Boyle realized that air wasn't nothing. It was a substance with weight and presence, necessary for sound, combustion, and life itself. Through these experiments, Boyle formulated what would later be known as Boyle's law. The pressure of a gas is inversely proportional to its volume. As volume shrinks, pressure grows. As volume expands, pressure decreases. This relationship remains fundamental to physics and chemistry to this day. As you settle into rest, picture the stillness of that vacuum chamber, utterly quiet, perfectly still. No sound, no fire, just the whisper of air being withdrawn, revealing secrets in the silence. In the vastness of nothing, Boyle found something essential. 16. Mesmer's animal magnetism. In the late 1700s, Franz Mesmer, a German physician, proposed a bold idea that an invisible fluid, which he called animal magnetism, flowed through all living beings and could be manipulated for healing. He believed this vital force could be directed or unblocked using magnets, or even his own hands. Mesmer's treatments involved theatrical displays. Patients would gather around a tub filled with iron filings and connected by cords, while Mesmer moved among them, waving his hands and staring into their eyes. Many reported strange sensations, fainting, convulsions, sudden relief from symptoms. To some, it seemed miraculous. To others, suspicious. Though science would eventually discredit animal magnetism as a physical force, Mesmer's influence endured. His dramatic style laid the groundwork for what would become hypnosis. And his belief in the mind's power to affect the body sparked deeper interest in psychosomatic medicine. As sleep gently takes hold, imagine Mesmer's darkened parlor, candlelight flickering across mesmerized faces, and a strange calm settling over the room. Though his fluid may not have existed, the power of suggestion, of belief, was real enough to change lives. 17. Halley's weather mapping from barometer readings. Better known for the comet bearing his name, Edmund Halley was also a pioneer in meteorology. In the late 1600s, he became fascinated with the idea of mapping air pressure to understand weather patterns. Using barometers, tools that measure atmospheric pressure, Halley collected readings from across regions and created some of the first weather maps. He noticed patterns, regions with consistent pressure, places where winds change direction, and how storms seemed to follow invisible pathways across the sea. His maps were rudimentary but groundbreaking, showing the global circulation of air, especially the trade winds crucial for navigation. This wasn't just academic curiosity. Halley's work helped ships sail more efficiently, anticipate storms, and understand monsoons. It was a step toward modern meteorology, toward seeing the sky not as chaos but as a system with patterns and logic. As your mind drifts, imagine the gentle rise and fall of pressure in the air around you, the invisible breath of the planet. Halley's maps brought order to the winds, tracing calm and storm alike on parchment. In those swirling lines, the weather first became something we could read. 18. Fahrenheit's mercury thermometer calibration. In the early 1700s, Daniel Gabriel Fahrenheit set out to solve a problem that had long plagued scientists: how to measure temperature accurately and consistently. Earlier thermometers used alcohol and often gave unreliable readings, affected by air pressure and impurities. Fahrenheit introduced mercury, a more stable liquid that responded uniformly to changes in heat, and with it, he crafted a thermometer that would change how we understand the world around us. But the real brilliance lay in his calibration. Instead of using arbitrary points, Fahrenheit chose repeatable reference events. He set the 0 point at the coldest brine mixture he could create using water, ice, and salt. He then used the melting point of ice and the average human body temperature as other anchors, setting his scale between them. This allowed for a consistent, repeatable range that didn't rely on guesswork. Though Celsius and Kelvin would later offer simpler or more scientific scales, Fahrenheit's system brought a level of precision that revolutionized medicine, weather forecasting, and daily life. Suddenly, people could describe warmth and coldness with numerical accuracy. As you relax tonight, imagine a slender glass tube filled with shimmering mercury, quietly rising and falling with the temperature of the room. A delicate tool born from a simple goal: to give shape to something invisible. In Fahrenheit's hands, heat found a scale, and the world found a way to measure comfort. 19. Cavendish's measurement of Earth's mass. In 1797, British scientist Henry Cavendish conducted an extraordinary experiment not to weigh the Earth with a scale, but to calculate its mass using gravity. Using a device called a torsion balance, Cavendish suspended a wooden rod with small lead spheres at each end. Larger lead spheres were placed nearby. The gravitational attraction between the small and large masses caused the rod to twist ever so slightly. By measuring this minuscule motion, Cavendish could calculate the gravitational force, and from that, the mass of the Earth. It sounds almost magical. He never touched the Earth or moved a mountain. Instead, he observed a barely there sway of a rod in a silent room. The results were astonishingly accurate for his time, determining the Earth's density within 1% of the modern accepted value. Cavendish's experiment didn't just measure Earth. It proved that gravity is not only a cosmic force acting on planets but also a subtle one acting between ordinary objects. It was a triumph of precision and patience. As you settle into sleep, imagine that delicate rod turning ever so slightly in a still, quiet room, moved by the invisible pull of mass upon mass. In that hushed motion, the weight of the world was revealed, not with clamor, but with calm. 20. Joule's paddle wheel heat experiment. In the mid-1800s, James Prescott Joule conducted a series of experiments to understand the relationship between work and heat. One of his most elegant involved a paddle wheel immersed in water. As weights dropped, they turned the paddle through a system of strings and pulleys, stirring the water. Joule carefully measured the water's temperature before and after the motion. What he discovered was groundbreaking. Mechanical energy had transformed into thermal energy. The falling weights performed work, and that work heated the water. This was one of the earliest proofs that heat wasn't some mysterious fluid, but a form of energy. Joule's findings laid the foundation for the first law of thermodynamics, the principle of energy conservation. Energy could not be created or destroyed, only transformed. His paddle wheel experiment, quiet and methodical, reshaped how we understand engines, the body, and even the universe. Joule was meticulous, repeating his experiments to reduce error and refine his conclusions. With each trial, he moved closer to unlocking a universal truth. As you drift off, imagine the gentle swirl of water stirred by falling weights, the room silent except for the soft splash of motion. Energy, in its simplest form, becoming warmth. In that still moment, Joule taught us that motion and heat are two sides of the same coin, and that every movement leaves a trace of warmth behind. 21. Michaelelsson-Moly ether experiment. In the late 19th century, scientists believed that light traveled through a mysterious medium called luminiferous ether, an invisible substance thought to fill the universe. To detect this ether, Albert Michaelelsson and Edward Moly designed one of the most sensitive experiments of their time. They built an interferometer, a device that split a beam of light into two paths at right angles, then recombined them to detect tiny differences in speed caused by Earth's movement through the ether. They expected to see a measurable shift, like a boat cutting through water. But time after time, their results showed nothing. The speed of light remained constant, no matter the direction of the Earth's motion. This result was baffling. Though it didn't confirm their original hypothesis, the experiment's importance can't be overstated. It dealt a fatal blow to the ether theory and paved the way for Einstein's theory of special relativity, which proposed that the speed of light is a universal constant. As you settle down, imagine the delicate balance of mirrors and beams, the quiet hum of scientific instruments searching for something that wasn't there. Sometimes, in science, the silence speaks louder than proof. The absence of evidence became a turning point, reshaping physics forever. 22. Young's double-slit light experiment. In 1801, Thomas Young performed a simple but astonishing experiment that would challenge centuries of thinking about the nature of light. He shone a beam of light through two closely spaced slits and observed the pattern it made on a screen behind them. What appeared wasn't two bright spots, as you'd expect from particles, but a series of alternating bright and dark bands, an interference pattern. This effect revealed something profound. Light behaves like a wave. The bright bands formed where the waves from each slit reinforced each other, and the dark ones where they cancelled out. It was like ripples on a pond overlapping and creating patterns. Until then, many believed light was made of particles, tiny corpuscles as Isaac Newton had suggested. But Young's experiment showed that light had properties of both waves and particles, a strange duality that remains a central mystery of quantum physics even today. Young's apparatus was basic, just sunlight, slits, and a screen, but the result was deep. The elegance of this experiment lies in its simplicity and the doors it opened. It showed how the universe could behave in ways far stranger than common sense might suggest. As you rest, imagine the soft shimmer of waves interfering on a quiet surface, creating delicate ripples of light and shadow. In those gentle patterns, the secret of light was whispered, not shouted. 23. Bacon's Ice Preservation Trials. In the 1600s, philosopher and early scientist Francis Bacon became fascinated with the idea of preserving meat using cold. At a time when refrigeration didn't exist, this was a bold and experimental idea. During a snowy day, Bacon stuffed a chicken with snow to see if the cold would slow decay. Tragically, the experiment led to him catching pneumonia, but it sparked centuries of exploration into food preservation. While the trial itself was rudimentary, the concept was revolutionary. Bacon had identified temperature as a key factor in preservation. It laid early groundwork for refrigeration science, even though the technology to make it practical wouldn't appear for centuries. Bacon's experiment wasn't just about chicken, it was about understanding decay, temperature, and how we could control natural processes to benefit society. His willingness to test his theories hands-on showed the spirit of early empirical science, curiosity backed by action. Though the experiment may seem quaint today, it represented a shift from relying solely on tradition and observation to engaging with the physical world through direct experimentation. As you fall asleep, imagine that snow-laden landscape, silent and still. Picture Bacon, bundled against the cold, determined to test his theory even in discomfort. In that frozen moment, science took one more step forward into the world of the practical. And in the hush of snow, a whisper of the modern age was born. 24. Volta's frog leg electricity tests, the spark that changed science. In the late 18th century, a seemingly strange phenomenon became the spark that would ignite the age of electricity. Luigi Galvani had noticed that when he touched the exposed nerves of a dead frog's leg with metal tools, the leg twitched as though it were alive. He believed this was proof of a new life force he called animal electricity. But one man, Alessandro Volta, had doubts. He suspected that the true source of the reaction lay not in the frog but in the metals themselves. To test his theory, Volta began experimenting with different combinations of metals, placing them in contact with frog tissue. Over time, he realized that the muscle contractions were triggered not by any vital force but by the contact between dissimilar metals and a moist conductor. This led to his construction of the first electrical battery, the voltaic pile. Using layers of zinc and copper separated by brine-soaked cloth, he produced a steady electric current, a feat never accomplished before. Volta's careful observation and rejection of accepted ideas led to one of the most critical breakthroughs in science. His work marked the transition from biological theories of electricity to mechanical and chemical understanding. It laid the groundwork for everything from electric lights to smartphones. And it all began with the quiet twitch of a frog's leg, observed by candlelight in a dusty laboratory. As you drift off tonight, imagine that flicker of motion becoming a pulse that changed the world. 25. Galens Dissections and Animal Vivisection, peering into the body's secrets. Long before modern medical schools and sterile laboratories, a curious mind in ancient Rome was uncovering the inner workings of the human body, without ever cutting one open. Claudius Galen, a Greek physician living in the 2nd century CE, faced strict cultural and religious prohibitions against dissecting human cadavers. Undeterred, he turned to animals, particularly pigs and monkeys, to unlock anatomical secrets that had remained hidden for centuries. In open-air theaters and private chambers, Galen performed vivisections, live dissections of animals, to demonstrate how organs worked. He traced the path of nerves, revealed the structure of muscles, and even mapped the brain and spinal cord. Observing how a cut nerve could cause paralysis or how pressing on the heart affected blood flow, he formulated ideas that would guide medical thinking for over 1,000 years. Galen believed that the body operated through a balance of 4 humors and that organs had distinct roles. While many of his theories were flawed, his observational techniques were pioneering. His writings became the cornerstone of medical education throughout the Middle Ages, influencing Islamic and European medicine alike. Though controversial and distressing by today's standards, Galens' animal dissections represent an early commitment to understanding the human body. He sought knowledge not for spectacle but for healing. So as you lie still tonight, think of Galen under torchlight, carefully lifting the veil on life's inner machinery, hoping to bring clarity where once there was only mystery. 26. Avogadros Gas Volume Studies, Equal Spaces, Equal Particles. In the quiet landscapes of 19th century Italy, a humble scientist named Amedeo Avogadro proposed an idea so simple and yet so profound that it would take decades for the world to recognize its brilliance. While experimenting with gases, Avogadro noticed a curious relationship. Under the same temperature and pressure, equal volumes of gases seem to contain equal numbers of molecules, regardless of their type. This elegant idea would come to be known as Avogadro's law. At the time, chemistry was still untangling the mysteries of atoms, molecules, and the invisible architecture of matter. Many scientists believed that gases combined in fixed proportions but didn't understand why. Avogadro suggested that gases weren't made of indivisible atoms alone but could exist as molecules, clusters of atoms bonded together. This explained why 2 volumes of hydrogen could combine with 1 volume of oxygen to make water, because the molecules themselves rearranged. Though largely ignored during his lifetime, Avogadro's insight laid the groundwork for modern chemistry. His work made it possible to calculate molecular weights, understand chemical reactions more precisely, and eventually define the famous Avogadro's number, the number of particles in 1 mole of a substance. Picture Avogadro working alone, scribbling notes by oil lamp, his mind filled with invisible particles dancing through space. His quiet observations would help humanity grasp the fundamental consistency of the universe. As you fall asleep, imagine the stillness of the air around you, and how, even in that silence, trillions of molecules are perfectly arranged, just as Avogadro imagined. 27. Gilbert's magnetized globe, Torella, modeling the magnetic Earth. In the late 1500s, long before satellites or compasses as we know them, English physician and natural philosopher William Gilbert sought to understand the strange force that guided navigators across oceans. People had noticed for centuries that compass needles pointed north, but why? To answer this, Gilbert created a small magnetic model of the Earth. He called it the Torella, or Little Earth. It was a sphere made of lodestone, a naturally magnetized mineral. By carefully observing how small compass needles moved around this miniature Earth, Gilbert found something astonishing. They behaved just as they would on the real planet. The compass needles aligned themselves along invisible lines that curved around the sphere, mirroring the way Earth's magnetic field directs navigation in real life. From this simple but ingenious experiment, Gilbert proposed that the Earth itself acts like a giant magnet. This was a groundbreaking idea at the time and laid the foundation for the science of geomagnetism. Before this, the nature of magnetic forces was cloaked in mystery and superstition. Gilbert's Torella was more than a clever model. It showed, elegantly and quietly, that scientific principles could be demonstrated using simple, physical objects, and that unseen forces could be mapped and understood. So as you drift off tonight, imagine that tiny sphere resting in candlelight, pulling little compass needles toward an unseen north, whispering secrets of the Earth's hidden magnetic soul through the soft hum of silent force. 28. Fleming's moldy petri dish observation, the accidental birth of penicillin. It was 1928, and Scottish bacteriologist Alexander Fleming had just returned from a vacation. As he inspected his cluttered laboratory, something curious caught his eye. A petri dish that had been left out, containing colonies of Staphylococcus bacteria, had grown a strange mold. Around that mold, the bacteria were gone. Wiped out. Where other dishes were swarming with bacterial life, this one had a clear halo of destruction. Most people might have discarded such a mess. But Fleming didn't. He looked closer. He realized that this common mold, Penicillium notatum, was releasing a substance that killed bacteria. What began as a spoiled experiment quickly became the spark for the most significant medical discovery of the 20th century, penicillin. Fleming's accidental observation would lead to the creation of antibiotics, transforming medicine and saving millions of lives from infections that had once been deadly. Yet, in that quiet moment, with dust in the air and the afternoon light slanting through glass, it was just a man, a dish, and some mold. He couldn't have known then how much this humble scene would change the course of history. The journey from that forgotten dish to life-saving medicine would take years, involving other scientists and wartime urgency, but it all started with an overlooked mold in an untidy lab. As you close your eyes, imagine that lonely dish on a forgotten bench, the silence of the room, and the power of nature quietly working its miracle, one tiny spore at a time. 29. Ørsted's compass needle deflection, electricity meets magnetism. In 1820, Danish physicist Hans Christian Ørsted was giving a routine lecture to his students. On the table before him were two common items, a wire connected to a battery and a small magnetic compass. What happened next would redefine physics forever. As he passed electric current through the wire, the compass needle suddenly moved, deflecting from its usual northward direction. Ørsted froze. He hadn't expected that. The electric current had created a magnetic field, and that field was affecting the compass. This was the first direct evidence that electricity and magnetism were connected. Ørsted had stumbled upon electromagnetism, an invisible dance of forces that no one had ever witnessed before. Until then, electricity and magnetism were considered completely separate. But this one moment showed they were linked, two aspects of a single, powerful phenomenon. Ørsted's discovery wasn't planned. He wasn't trying to unify physical laws. But by observing, pausing, and trusting his curiosity, he opened the door to a new world, one that would later inspire the work of Faraday, Maxwell, and ultimately Einstein. His finding led to the invention of electromagnets, electric motors, generators, and the entire modern electrical infrastructure that powers your world. But it all began with a trembling compass needle and the quiet realization that unseen forces were at play. So as you drift off tonight, imagine the still air of a lecture hall, a simple wire, a flickering candle, and a needle that dares to move, not from wind or touch, but from the silent hum of invisible energy. 30. Miller's primordial soup experiment, simulating the birth of life. In 1952, deep in the University of Chicago's chemistry lab, two scientists, Stanley Miller and Harold Dewey, set out to answer one of humanity's oldest questions: how did life begin? Could the building blocks of life form from the conditions of early Earth, without any living organisms present? Their experiment became one of the most fascinating and imaginative scientific tests ever performed. They built a closed glass system that mimicked Earth's ancient atmosphere, filled with water vapor, methane, ammonia, and hydrogen gas. Then, they introduced an electric spark, simulating lightning strikes that might have occurred in primordial storms. 4 days, the mixture bubbled and sparked. Then something remarkable happened. At the bottom of the device, a brownish sludge began to appear. When analyzed, it contained amino acids, the fundamental components of proteins, and by extension, life itself. From gases and sparks alone, the experiment had created the building blocks of biology. It was dubbed the primordial soup, a poetic name for this strange chemical stew that might have been the first step toward life. Though the exact origins of life remain a mystery, Miller's experiment proved that the raw materials of life can emerge from simple chemical reactions. As you close your eyes, imagine the quiet bubbling of strange gases, the crackle of artificial lightning, and the dark, mysterious liquid pooling at the bottom of the flask, suggesting that perhaps, in a world of storms and gases, life could begin not with a whisper, but with a spark. 31. Archimedes and the Golden Crown Buoyancy Test. In the still waters of ancient Syracuse, a mystery once troubled the mind of the brilliant thinker Archimedes. The king had gifted a crown of gold to the gods, but whispers of deceit arose. Was the crown pure gold, or had the goldsmith mixed in silver to cheat the king? With no tools to melt it down or damage the crown, Archimedes had to find another way to uncover the truth. Legend says he found the answer while slipping into a bath. As his body sank into the water, he noticed the water level rise. That simple observation led to a profound realization: objects displace water equal to their own volume. If the crown had silver hidden inside, it would displace more water than a crown made of pure gold, because silver is less dense. Archimedes leapt from his bath shouting, "Eureka! I found it!" This moment marks one of the earliest known uses of a scientific principle to solve a real-world problem. Archimedes didn't need advanced tools or elaborate machines, just observation, reasoning, and a quiet moment in the bath. His buoyancy principle became a cornerstone of fluid mechanics and still holds true today. As you gently relax and let your mind float, picture Archimedes stepping into warm water, his eyes lighting up with discovery. A mystery solved not with force or fire, but with the stillness of thought and the silence of water rising in a tub. Underscore 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 underscore. 32. Torricelli's Mercury Barometer. Imagine a quiet room in the 1600s, lit by a flickering candle, with mercury glistening in a glass tube. Evangelista Torricelli, a student of Galileo, had been pondering a strange mystery. Why couldn't water be pumped higher than 10 meters? The answer, it turned out, had nothing to do with water at all, but with air. Torricelli filled a long glass tube with heavy mercury, then inverted it into a dish. To his amazement, the mercury didn't fall completely out. Instead, a space formed at the top of the tube, what we now know as a vacuum. The mercury held steady, balanced by the invisible pressure of the air outside the tube. With this simple act, Torricelli had invented the first barometer, and with it, revealed that air has weight. This was a groundbreaking idea. Until then, many believed air was weightless, or that nature simply abhors a vacuum. Torricelli's experiment showed that atmospheric pressure could be measured, and that it changed. As pressure dropped or rose, so did the mercury in his tube, foreshadowing storms or clear skies. Tonight, as you breathe deeply and calmly, consider the quiet power of the invisible air that surrounds us. Each gentle breath you take presses softly against your skin, a silent ocean of atmosphere that Torricelli gave us the tools to measure. His mercury barometer didn't just measure pressure, it marked the beginning of modern meteorology and opened a door to understanding the unseen forces that shape our world. Underscore 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 underscore. 33. Boses Plant Response to Stimuli. In the late 19th century, nestled in a serene corner of colonial India, Jagadish Chandra Bose was busy listening, not to voices, but to plants. Most thought plants were passive, almost lifeless. But Bose had a different idea. He believed that plants could sense, feel, and respond to the world around them, and he set out to prove it with quiet precision. Using instruments of his own invention, Bose created delicate devices that could measure the tiniest movements in plant tissues. He showed that plants reacted to light, heat, cold, and even the prick of a needle. His experiments revealed that when a plant leaf was injured, it sent signals, tiny electrical impulses, just like nerves in animals. This was revolutionary. In a time when plants were viewed as simple green machines, Bose's work suggested something more poetic, that plants have a form of life and awareness, a subtle language of movement and electricity. He even placed a plant near chloroform and watched it slowly fall asleep, then recover, as if it had taken a nap. So, as you relax tonight, picture a garden gently swaying under moonlight. Every leaf and stem is quietly aware, softly sensing the world, just like you. Boses' gentle experiments didn't just challenge science, they offered a reminder that even the quietest life forms hold secrets waiting to be discovered. His work whispers to us still that life, in all its forms, is more connected, more aware, and more beautiful than we often stop to realize. 34. Leeuwenhoek's single-lens microscope studies. In the late 1600s, a Dutch tradesman named Antony van Leeuwenhoek peered into a world no human had ever seen before. Using a simple single-lens microscope he crafted himself, no more complex than a magnifying glass mounted on a pin, he revealed the teeming universe of what he called animalcules. These were, in fact, bacteria, protozoa, and other microorganisms. Leeuwenhoek had no formal scientific training, yet he possessed two things most others lacked: intense curiosity and extraordinary patience. He ground tiny lenses with such precision that they could magnify objects up to 270 times, far surpassing the compound microscopes of his time. With this humble tool, he examined pond water, blood, dental plaque, and even his own bodily fluids. In doing so, he became the first person in history to observe living single-celled organisms. He described their shapes and movement with vivid detail, often sketching them for the Royal Society of London, which initially received his letters with skepticism. But repeated verification affirmed his discoveries. His findings laid the foundation for microbiology, a field that would remain dormant for centuries before blossoming in the 19th century. Leeuwenhoek's work wasn't just a glimpse into the invisible, it was a challenge to the understanding of life itself. Though he never theorized deeply about what he saw, his observations quietly whispered a profound truth: life is far more complex and hidden than it appears. He opened a microscopic window into the vast, unseen fabric of the world. 35. Darwin's Earthworm Movement Observations. Long after writing on the origin of species, Charles Darwin turned his attention to a less glamorous, but curiously vital, subject: earthworms. In the 1870s, in the twilight of his career, Darwin conducted a series of meticulous experiments to understand how these humble creatures contributed to the formation of soil. With the same patience and precision that had guided his earlier evolutionary work, Darwin observed the silent engineers of the earth, noting how they dragged leaves into their burrows and churned the soil with ceaseless dedication. He designed gentle experiments in his garden, placing leaves in various orientations and observing which ends the worms pulled first. He recorded their preferences and habits, showing that they weren't simply burrowing mindlessly, but exhibiting a form of primitive decision-making. He even tracked the rate at which earthworms buried ancient Roman ruins on his property, a slow but persistent process of natural recycling. In 1881, Darwin published his findings in The Formation of Vegetable Mold Through the Action of Worms, a book that surprisingly became a bestseller. It was the last of his publications, and though it lacked the drama of his evolutionary theory, it profoundly highlighted the role of minute creatures in shaping ecosystems. Earthworms, Darwin believed, were nature's silent workers, vital to plant life and agriculture. His quiet studies reminded the world that even the most overlooked beings play crucial roles in maintaining the balance of life. With these experiments, Darwin once again showed that science begins with attention, patience, and wonder, even when staring at the dirt. 36. Wuha's urea synthesis from inorganic compounds. In 1828, German chemist Friedrich Wöhler made a discovery that quietly shattered a major philosophical belief of his time. Up until then, scientists widely held that organic compounds, those found in living organisms, could only be produced by a mysterious, vital force unique to life. This belief separated the living world from the inorganic, drawing a strict line between what was natural and what could be synthesized in a lab. But Wöhler was about to cross that line. While working with ammonium cyanate, an inorganic compound, he accidentally produced urea, a substance found in urine and unmistakably organic. No animal, no plant, just chemicals and a little heat, and suddenly something from the realm of biology had emerged from the realm of chemistry. His discovery, though modest in appearance, was revolutionary in implication. Wuha's results stunned the scientific community and laid the groundwork for the birth of organic chemistry as a serious discipline. It meant that life's building blocks were not made by magic or essence but could be understood, studied, and even created through known chemical processes. Though Wuha himself did not claim to disprove vitalism outright, his work quietly unstitched the seams of a long-standing dogma. His simple synthesis pointed the way toward the understanding that all matter, living or not, obeyed the same physical laws. It was a turning point, where alchemy gave way to chemistry, and the laboratory became a place where life itself could be decoded. 37. Herschel's infrared radiation discovery. In 1800, astronomer William Herschel made an astonishing discovery while exploring sunlight with a prism. He was curious about the temperature of different colors in the visible spectrum. Using thermometers, he measured the heat of each color by placing the instruments just below the refracted light coming through the prism. Unexpectedly, the thermometer placed beyond the red part of the spectrum, where no visible light could be seen, showed the highest temperature. Herschel had stumbled upon something invisible to the eye: infrared radiation. This discovery marked the first identification of light beyond the visible spectrum. Before this, it was believed that sunlight only delivered visible illumination. Herschel proved that light also carried invisible forms of energy. His experiment was simple yet profound, involving little more than glass prisms and thermometers, but it opened up an entirely new realm of physics and astronomy. The implications were vast. This was the beginning of the understanding of electromagnetic radiation, leading to discoveries like radio waves, X-rays, and microwaves. Herschel's work laid the foundation for technologies such as night vision, remote sensing, and thermal imaging. While today we take for granted that the universe contains light our eyes can't see, Herschel's discovery was a pivotal moment in revealing the hidden dimensions of nature. It reminds us that just because something is invisible doesn't mean it lacks power. Through one quiet, meticulous experiment, Herschel expanded our vision, quite literally, into the unseen world that surrounds us, even as we drift off to sleep. 38. Fizeau's speed of light measurement. In 1849, French physicist Hippolyte Fizeau designed a clever experiment to measure something once thought unknowable: the speed of light. Rather than using distant celestial bodies or complex astronomical calculations, he turned to a more mechanical approach involving a toothed rotating wheel, a beam of light, and a mirror placed several kilometers away. Fizeau directed a beam of light through the rotating wheel so that the light passed between the teeth, traveled to the mirror, and reflected back. By adjusting the speed of the wheel, he discovered a point at which the returning light was blocked by the next tooth, effectively causing the beam to disappear. This vanishing point gave him the key to calculate how long the light took to travel to the mirror and back. From this simple yet ingenious setup, Fizeau calculated the speed of light to be approximately 313,000 kilometers per second, astonishingly close to the modern value of about 299,792 kilometers per second. What made Fizeau's experiment remarkable was not just its accuracy but its creativity. It proved that even something as elusive and fast as light could be measured with the right tools and patience. This measurement provided a foundational constant for future work in physics, particularly in Einstein's theory of relativity. Fizeau's wheel and mirror setup may sound quaint today, but it stands as a monument to human curiosity and precision, offering a timeless lesson. Sometimes, understanding the universe begins with a spin of a wheel and a beam of light. 39. Haldane's decompression chamber tests. In the early 20th century, British scientist John Scott Haldane ventured into the invisible dangers of deep-sea diving and pressurized environments. At the time, many divers suffered from a mysterious and painful affliction known as the bends or decompression sickness. This condition occurred when divers ascended too quickly, causing nitrogen bubbles to form in their bloodstreams. Determined to solve this mystery, Haldane built a decompression chamber and subjected animals, and even himself, to varying levels of pressure to simulate deep dives. He carefully monitored how gases dissolved and came out of solution in the body during pressure changes. Through meticulous experimentation, Haldane discovered that staged decompression, ascending in controlled, step-by-step intervals, allowed nitrogen to safely exit the body, preventing the bends. He went on to develop the first decompression tables, which revolutionized diving safety. Haldane's work also laid the groundwork for modern hyperbaric medicine and space physiology, as understanding how the body responds to extreme pressure and gas exchange is vital in many fields. His willingness to place himself at risk in the name of science showed extraordinary dedication. Haldane's decompression experiments may not sound flashy, but they have quietly saved thousands of lives. From deep-sea divers to astronauts, the principles he uncovered continue to protect human life in extreme conditions. As you relax and breathe evenly tonight, consider how much of our safety in unforgiving environments comes from Haldane's slow, steady, and brave experimentation, a true testament to science in service of survival. 40. Romer's temperature scale with alcohol. In the early 1700s, when the modern thermometer was still in its infancy, a French scientist named René-Antoine Ferchot de Romer sought to bring order to the chaos of temperature measurement. The devices of the time were unreliable and inconsistent. Some used water, others used air, and each had its own scale. Romer decided to solve this problem by developing a more standardized system using alcohol as the key liquid. Alcohol had a major advantage over water. It expanded and contracted more reliably across a wide range of temperatures. Romer created a scale where 0 was the freezing point of water and 80 degrees marked the boiling point. This scale was both easy to read and reproducible. The use of alcohol made the thermometer safer than mercury, especially in colder climates, where alcohol remained liquid even in freezing conditions. Although the Romer scale eventually fell out of favor, replaced by the Celsius and Fahrenheit systems, it had a significant impact. It brought early standardization to scientific and culinary practices, especially in Europe. In fact, for over a century, many dairies and breweries used Romer's scale to ensure precision in their craft. When you think of temperature today, you probably think of Celsius or Fahrenheit. But in the quiet, careful work of Romer's alcohol thermometers, we see the origins of modern measurement. It's a reminder that even the way we feel warmth or cold today was once a question in need of a curious mind and a thoughtful experiment. 41. Bernoulli's airflow tube demonstration. In the 18th century, Swiss physicist Daniel Bernoulli introduced a strange and fascinating idea that faster-moving air creates lower pressure. This concept, known as Bernoulli's principle, would go on to explain everything from how airplanes fly to why a shower curtain billows inward when the water runs. But in its infancy, it was proven through a surprisingly simple experiment using nothing more than a curved tube and some flowing air. Bernoulli set up a device called a venturi tube, a narrow section of pipe connected to wider ends. As air passed through this narrow segment, its velocity increased and its pressure dropped. Using manometers, which are devices that measure pressure, he could demonstrate that the pressure in the constricted section was indeed lower. It was a subtle but profound result, suggesting that air behaves much like a flowing fluid, and that energy within the flow is conserved but changes form. This deceptively simple demonstration laid the foundation for the field of fluid dynamics. Engineers would later use Bernoulli's insights to design better chimneys, carburetors, and ultimately aircraft wings. Though the experiment itself may not seem dramatic, its implications were revolutionary, rippling through physics and engineering for centuries. As you drift to sleep, imagine air whispering through tubes, revealing secrets about pressure and motion. Bernoulli's quiet experiment helped humanity understand invisible forces that swirl all around us, a reminder that even the air has stories to tell, if only we watch it closely enough. 42. Galvani's dead frog leg sparks. In a darkened 18th century lab, an Italian scientist named Luigi Galvani performed an experiment that shocked the world, quite literally. While dissecting a frog, Galvani noticed something peculiar. When he touched the exposed nerve of the frog's leg with a metal scalpel, the leg twitched as if alive. What was more astonishing was that the frog was long dead. This strange phenomenon ignited Galvani's curiosity and led to one of the first studies of what we now call bioelectricity. To investigate further, Galvani attached metal wires to frog legs and exposed them to different conditions. He discovered that when a wire made of two different metals was connected from a nerve to a muscle, the frog leg would jump. He believed that this animal electricity was stored within the tissues of the animal, like some natural battery. Though his interpretation wasn't entirely accurate, he was on to something remarkable. Galvani's work paved the way for Alessandro Volta to invent the first true electric battery, and for scientists to explore the relationship between electricity and the nervous system. Today, we understand that electrical signals are essential for everything from heartbeat rhythms to brain activity. Picture, as you drift off, the stillness of a laboratory table, the gentle twitch of a frog's leg, and the wonder of early scientists uncovering the secret currents of life itself. Galvani's spark wasn't just a flicker in a frog, it was the beginning of a revolution in understanding the body as an electrical being. 43. Lister's antiseptic spray in surgery. In the mid-1800s, surgery was a gamble. Even successful operations often led to deadly infections afterward. The air in operating rooms was thought to be harmless, and cleanliness was not yet considered a priority. But a quiet revolution was brewing in the hands of a British surgeon named Joseph Lister. Influenced by Louis Pasteur's work on germs, Lister began to wonder if invisible microorganisms were causing post-surgical infections. His answer came through a mist of carbolic acid. Lister devised a method of spraying carbolic acid, a form of phenol, into the air during surgery. He also applied it to wounds, dressings, and surgical tools. At first, the idea seemed extreme and even unnecessary to other doctors. But Lister kept meticulous records and noticed something striking. Infection rates dropped dramatically. His antiseptic technique was met with skepticism, even ridicule, but Lister's results were undeniable. Over time, more surgeons began adopting his practices, and lives were saved in staggering numbers. Surgery became safer, and modern sterile techniques owe their foundation to Lister's carbolic spray. Imagine drifting to sleep in a world before sterile gloves and disinfectants, where one man quietly changed everything with a bottle of mist. The hiss of the carbolic spray became a whisper of hope in operating theaters. Lister's experiment didn't just reduce infection, it redefined the boundaries between life, death, and the invisible world in between. 44. Becquerel's fogged photographic plate, radiation. In 1896, a curious French physicist named Henri Becquerel was fascinated by phosphorescence, materials that glowed after being exposed to sunlight. Inspired by Wilhelm Röntgen's discovery of X-rays, Becquerel hoped to find a link between sunlight and invisible radiation. He wrapped photographic plates in black paper, placed a piece of uranium salt on top, and left them in the sun. As expected, the plates became fogged, likely due to some kind of radiation. But then, nature surprised him. A stretch of cloudy days halted his experiment, so Becquerel stored the wrapped plates and uranium in a dark drawer. Later, on a whim, he developed the plates anyway. To his astonishment, they were still fogged. Somehow, without sunlight, the uranium had emitted something powerful enough to penetrate the black paper and expose the plate. This unintentional discovery revealed a mysterious form of energy we now call radioactivity. Becquerel had stumbled upon a force deep within matter itself, an invisible energy constantly being released. His accidental fogged plate marked the first proof that atoms were not as stable or inert as once believed. Soon after, Marie and Pierre Curie would expand on his work, isolating radioactive elements like polonium and radium. As you close your eyes, imagine a drawer in a quiet lab, where darkness reveals something more powerful than light. Becquerel's forgotten film strip showed that even in stillness, the universe hums with unseen energy, waiting patiently for curious minds to listen. 45. Bose oil drop on water surface study. Long before his quantum leaps into atomic theory, the Danish physicist Niels Bohr conducted a subtle yet fascinating experiment involving something as ordinary as oil and water. In his early academic years, Bohr set out to determine just how thin an oil film could be while still covering a measurable area. It was a deceptively simple question that required both creativity and care. Bose placed a known volume of oil onto a calm surface of water and observed how it spread out into a thin, even layer. Because the oil formed a monomolecular film, only one molecule thick, he could calculate the approximate diameter of an oil molecule based on how far the oil spread. This experiment was a beautiful example of using the macroscopic world to measure something microscopic. The simplicity of Bose's method hid its brilliance. With just oil, water, and some careful measurements, he bridged the gap between the seen and the unseen. His work laid groundwork for atomic-scale thinking, which would later define his career in quantum mechanics. As you drift off to sleep, think of a still pond and a single drop of oil, gently expanding until it becomes impossibly thin. In that fragile shimmer, young Bose glimpsed the hidden order of molecules. His oil drop study reminds us that sometimes, the most profound truths begin with the smallest questions, and answers ripple quietly across the surface of the unknown. 46. Maupertuis's flattening of Earth at the poles. In the early 18th century, the shape of the Earth was a subject of hot debate. Some believed it was a perfect sphere, while others suspected it bulged at the equator and flattened at the poles. Pierre-Louis Moreau de Maupertuis, a French mathematician and philosopher, set out to resolve the issue once and for all, not with theory, but with boots on the ground and measurements in hand. To prove Newton's prediction that the Earth was oblate, Maupertuis led a scientific expedition to the Lapland region near the Arctic Circle in 1736. There, he and his team measured the length of a degree of latitude. The idea was that if the Earth were truly flattened at the poles, a degree of latitude would span a longer physical distance near the poles than it would at the equator. After months of enduring frigid temperatures and physical hardship, Maupertuis collected enough data to support Newton's theory. His measurements showed that the Earth was indeed slightly flattened at the poles. This was not just a win for Maupertuis but a powerful victory for observational science and the Newtonian model. As you drift into sleep, picture snowy Lapland skies and quiet nights spent gazing upward, measuring the planet 1 degree at a time. Maupertuis's expedition wasn't merely about Earth's shape, it marked a shift toward empirical science, where nature reveals its secrets not through guesswork, but through cold, careful exploration. 47. Paracelsus's use of mercury for syphilis. In the Renaissance era, medicine was still deeply intertwined with mysticism and ancient doctrine. Diseases were seen as divine punishments or imbalances of humors. But then came Paracelsus, a Swiss physician and alchemist with a rebellious streak and a radical idea that chemicals, not just herbs or spiritual remedies, could be used to treat disease. One of his most controversial treatments involved the use of mercury to combat syphilis, a sexually transmitted disease that was ravaging Europe at the time. Paracelsus observed the horrible effects of syphilis and dared to try mercury, a substance known for its toxicity, as a remedy. Applied topically or given in small doses, mercury appeared to reduce the symptoms. Though extremely dangerous and not a cure by modern standards, this approach offered relief where none had existed. It challenged prevailing beliefs that only natural, non-metallic substances were safe for the body. This early use of chemicals in medicine paved the way for modern pharmacology. Paracelsus's boldness helped usher in a new mindset, that the dose makes the poison, and even dangerous substances could be healing if used wisely. His emphasis on observation over tradition made him a father of toxicology. As you settle into rest, think of flickering candlelight over ancient flasks, and a lone doctor questioning centuries of medical wisdom. Paracelsus's mercury trials were more than medicine, they were a declaration that healing could evolve, even if the road was risky and lined with mercury. 48. Binet's early intelligence testing. In the bustling classrooms of late 19th century France, educators faced a dilemma. How could they identify students who needed extra help without relying on arbitrary judgments or guesswork? Into this problem stepped Alfred Binet, a French psychologist with a deep curiosity about the human mind. Binet believed that intelligence wasn't fixed or absolute but could be measured in meaningful, practical ways. His pioneering solution was to create the world's first standardized intelligence test. Binet, along with his collaborator Theodore Simon, designed a series of tasks and questions tailored to the cognitive abilities of children. These ranged from simple problem-solving and memory recall to tasks involving attention and comprehension. The goal was not to rank students but to identify those who might benefit from special educational support. Binet introduced the idea of mental age, allowing comparisons between a child's intellectual development and their actual age. The Binet-Simon scale laid the groundwork for all modern IQ tests, though Binet himself warned against using such tests as definitive labels. He feared they could be misused to limit children's potential rather than nurture it. Sadly, his caution was often ignored. As you close your eyes, imagine quiet schoolrooms where minds are being gently understood, not judged. Binet's work was a quiet revolution in empathy, a belief that intelligence could be explored with care and nuance. His test was not about numbers, but about unlocking possibilities hidden within every growing mind. 49. Galton's fingerprint classification. In the late 19th century, British scientist Francis Galton found himself captivated by the mysterious patterns etched into the tips of human fingers. While fingerprints had long been observed as unique, no one had formally studied or categorized them. Galton, a cousin of Charles Darwin and a polymath in his own right, saw potential in these ridges, not just as curiosities, but as identifiers. Galton began collecting thousands of fingerprints and analyzing them with scientific precision. He identified 3 primary patterns: loops, whorls, and arches. More importantly, he developed a classification system that allowed fingerprints to be compared and stored systematically. His work demonstrated that the chance of 2 individuals having identical fingerprints was astronomically small. While Galton didn't invent fingerprinting for identification, his methodical approach laid the groundwork for its widespread forensic use. Police forces around the world soon adopted fingerprint analysis as a reliable means of identifying suspects. It transformed detective work from intuition to evidence-based investigation. As you drift into slumber, think of quiet study rooms filled with ink-smudged cards and magnifying glasses, where invisible truths slowly revealed themselves in spirals and ridges. Galton's fingerprint classification turned the simple touch of a fingertip into an undeniable signature of identity, proving that even the smallest parts of us carry unique stories. 50. Wundt's reaction time measurements. In a quiet Leipzig laboratory in the late 1800s, Wilhelm Wundt was building something radical, the very first psychological laboratory. While philosophers had long pondered the mind, Wundt sought to measure it. He believed that mental processes could be broken down into components and studied scientifically. One of his first tools? A simple device for measuring reaction time. Wundt and his assistants used metronomes, clocks, and sound stimuli to test how quickly a person could respond to a specific cue, like pressing a button after hearing a tone. Though basic by modern standards, this method allowed Wundt to isolate perception, attention, and consciousness. He concluded that even a few hundred milliseconds could reveal much about how the brain processes information. These experiments formed the foundation of experimental psychology. By introducing controlled measurements and repeatable procedures, Wundt legitimized psychology as a scientific discipline. His reaction time studies, though simple, opened the door to understanding the tempo of thought and the machinery of the human mind. As you ease into sleep, imagine the tick of a metronome and the flick of a hand recording silent mental rhythms. Wundt's tiny time gaps whispered profound truths, that even our fleeting reactions could be studied, timed, and understood. His work invites us to see our minds not as mysteries, but as elegant systems, pulsing quietly beneath our awareness. 51. Asker's conformity line experiment. In 1951, psychologist Solomon Asch conducted a deceptively simple experiment that would reveal how social pressure can shape perception. Volunteers were shown a card with 1 line, followed by another card with 3 lines labeled A, B, and C. Their task was to identify which of the 3 lines matched the first in length. It seemed straightforward, until the twist. Each participant was seated in a group with actors who had been instructed to unanimously give the wrong answer on certain trials. The real subject, unaware of the deception, would typically respond last. Ask found that a surprising number of participants conformed to the incorrect group consensus, even when the answer was obviously wrong. This simple experiment revealed something profound. People often go along with the group, even if it contradicts their own senses. The desire to fit in or avoid conflict can override reason. Aska's findings sent ripples through psychology, showing that perception is not only shaped by our senses but also by our social surroundings. Picture a quiet room, a row of faces, and a single honest answer wavering under the weight of the crowd. As you fall asleep, let this experiment remind you of the delicate balance between self and society. Aska's lines weren't just about vision, they traced the invisible influence others have over our thoughts, and the quiet courage it takes to stand alone in truth. 52. Zimbardo's Stanford Prison Experiment. In the summer of 1971, psychologist Philip Zimbardo conducted a dramatic experiment in the basement of Stanford University's psychology building. What was intended as a simple 2-week simulation of prison life quickly spiraled into one of the most haunting psychological studies ever recorded. Volunteers were assigned randomly to play the roles of either guards or prisoners, and a mock prison was built to mimic the real thing. What unfolded was shocking. Within days, the guards, previously normal college students, began exhibiting cruel and authoritarian behavior. They devised punishments, enforced rigid rules, and psychologically tormented the prisoners. The prisoners, in turn, became submissive, anxious, and emotionally distressed. Zimbardo, acting as the prison superintendent, allowed the experiment to continue until outside observers were alarmed by the deteriorating conditions. It was shut down after just 6 days. The Stanford Prison Experiment revealed the frightening ease with which ordinary people could adopt abusive behaviors when placed in positions of power. It highlighted the powerful influence of situational factors over individual morality. Though later criticized for ethical concerns and lack of scientific rigor, the study remains a chilling reminder of how context can override conscience. As you sink into sleep, imagine the sterile hum of fluorescent lights, the shuffle of feet down a corridor, and the quiet collapse of identity under pressure. Zimbardo's prison was more than an experiment. It was a mirror held up to the darkest corners of human behavior, reminding us that under the right conditions, anyone might wear a mask they never imagined. 53. Milgram's Obedience to Authority Test. In the early 1960s, psychologist Stanley Milgram set out to understand a harrowing question: how far would an ordinary person go in obeying authority, even if it meant causing harm to another? The backdrop was chilling. The recent Holocaust had revealed the devastating consequences of blind obedience. Milgram's approach was straightforward but deeply unsettling. Participants believed they were part of a study on learning and memory. They were instructed to administer electric shocks to another participant, a learner, each time a wrong answer was given. Unbeknownst to them, the learner was an actor, and no real shocks were given. As the shocks supposedly intensified, reaching dangerous levels, many participants hesitated. But when prompted by an authority figure in a lab coat, most continued. A shocking number of participants obeyed to the end, even as the learner screamed, pleaded, or fell silent. Milgram's experiment demonstrated the disturbing power of authority and the ease with which individuals can commit harmful acts when instructed by someone in charge. Though controversial, the study revealed that obedience isn't simply a matter of character, but of context and pressure. As you rest tonight, think of quiet rooms and ticking switches, and the fragile line between morality and command. Milgram's experiment reminds us that the capacity to harm does not reside in monsters. It lives quietly, waiting in the shadow of authority, and must be guarded against with awareness and courage. 54. Harlow's Wire Mother Monkeys. In the 1950s, American psychologist Harry Harlow sought to answer a profound question: what truly forms the bond between a child and its mother? At the time, many believed that attachment came primarily from feeding. To test this, Harlow conducted a series of controversial but illuminating experiments using infant rhesus monkeys. He created 2 artificial mother figures, one made of bare wire that dispensed milk, and another covered in soft cloth that offered no food. Baby monkeys were placed in cages with both options. Despite their need for nourishment, the monkeys overwhelmingly clung to the cloth mother, seeking comfort, warmth, and security from the soft texture. When frightened, they ran to the cloth figure, not the one that fed them. Harlow's research revealed that emotional comfort was more important than sustenance in forming strong attachments. His work helped shift the understanding of child development, emphasizing the need for affection, touch, and emotional care. It challenged sterile parenting norms and informed better practices in childcare, adoption, and orphanage systems. As you drift off, imagine a small, frightened monkey in a quiet cage, reaching not for food, but for a soft embrace. Harlow's wire mothers taught us that love is more than biology. It's built on presence, warmth, and connection. In those tiny, trembling arms, science found proof that to be held is to be human, and that comfort may be the deepest nourishment of all. 55. Skinner's Operant Conditioning Box. In the quiet corners of B.F. Skinner's laboratory, a small box changed the way we understand behavior. This unassuming device, later known as the Skinner box, allowed researchers to study how actions are shaped by consequences. Inside, a rat or pigeon might press a lever and receive a food pellet. Or perhaps pressing the lever stopped an annoying sound. Over time, the animals learned to press the lever more or less depending on what followed that action. Skinner called this learning process operant conditioning, and it was revolutionary. Unlike Pavlov's classical conditioning, which focused on automatic responses, Skinner explored voluntary behavior and how it could be reinforced or discouraged. Positive reinforcement, negative reinforcement, punishment, all these tools became part of a growing psychological toolkit to shape behavior. The simplicity of the experiment belied its deep implications. It laid the groundwork for everything from animal training to educational methods, even influencing workplace structures and parenting strategies. Skinner suggested that much of human behavior could be understood not as free will, but as patterns shaped by reinforcement histories. His ideas stirred controversy but also inspired generations of psychologists and educators. Late at night, as the quiet whir of the box filled the lab, small behaviors were being recorded that would ripple through psychology for decades. In those repetitive actions of rats and birds, Skinner saw a mirror of human complexity, a reflection of how, without even realizing it, we all respond to the gentle pushes and pulls of consequence. 56. Gibson's Visual Cliff Experiment. Imagine being a baby placed on a flat surface that suddenly seems to disappear into a deep drop. That was the ingenious setup Eleanor Gibson and Richard Walk created in 1960 to study depth perception. Their visual cliff experiment used a glass table with a checkerboard pattern underneath one side, and the same pattern placed much lower on the other side. Although both sides were equally solid, visually, one appeared to be a steep drop, a cliff. When infants or baby animals were placed on the shallow side, researchers watched to see whether they would crawl across the glass toward their caregiver or avoid the cliff. Most babies, once old enough to crawl, refused to cross the apparent drop. Even young animals like chicks and goats showed similar hesitations. The conclusion? Depth perception appears to be at least partially innate rather than learned. The implications rippled beyond infant development. The experiment suggested that certain survival instincts are hardwired, and perception develops earlier than previously thought. It challenged the idea that all behaviors are learned through experience, pointing instead to a blend of biology and environment. For decades, the visual cliff experiment remained a powerful example of how cleverly designed research could peel back the layers of human perception. As parents watched their babies pause at the edge of an invisible drop, they weren't just seeing hesitation. They were witnessing the emergence of one of our most fundamental tools for survival, the ability to perceive and respond to the world in 3 dimensions. 57. Loftus's misinformation effect. In the dim light of memory, details shift more easily than we'd like to believe. Psychologist Elizabeth Loftus revealed this unsettling truth with her groundbreaking work on the misinformation effect. Through a series of experiments beginning in the 1970s, she demonstrated that human memory is not only fragile but surprisingly easy to manipulate. In one well-known experiment, participants watched a film of a car accident. Later, they were asked leading questions: how fast were the cars going when they smashed into each other? Some were asked with milder words like hit or bumped. The results were startling. Those who heard the word smashed estimated higher speeds and were more likely to report seeing broken glass, even though there wasn't any. Just a single word had reshaped their memory. Loftus's work shook the foundations of eyewitness testimony, once considered the gold standard in courtrooms. Her findings suggested that memories are not perfect recordings but are reconstructed each time we recall them, leaving them vulnerable to suggestion. This had profound implications for justice, therapy, and even journalism. Loftus warned against the dangers of implanted memories, especially in cases of recovered childhood trauma. Her courage in confronting controversial issues sparked debates and reforms across multiple disciplines. In the quiet space where memory and suggestion meet, Loftus revealed a paradox. The more confident we are in our recollections, the more likely they are to be influenced. Her work taught us to treat memory not as a fixed archive, but as a living, shifting story. 58. Tolman's cognitive map in rats. In the quiet corridors of early behavioral psychology, Edward Tolman charted a course that challenged the rigid stimulus-response framework of his time. In the 1940s, he introduced an idea that was both radical and elegant: that rats, and by extension, other animals including humans, don't merely respond to stimuli like machines. They think. They form mental maps. To prove this, Tolman designed a simple yet profound experiment. He placed rats in a maze with various pathways, some leading to food, others to dead ends. When a route was blocked, rather than panicking or wandering randomly, many rats chose alternative paths that still led them to the goal, even those they hadn't been rewarded for taking before. This suggested they had developed a cognitive map of the environment in their minds, navigating with an internal sense of direction rather than trial and error conditioning. Tolman's work quietly upended the dominant behaviorist views, which denied the importance of internal mental states. His findings laid the groundwork for what would become cognitive psychology, a field that appreciates the brain as an active processor of information. In essence, Tolman reminded us that learning isn't just about repetition and reinforcement, it's about perception, insight, and memory. His maze-running rats opened a window into the complexity of animal and human thought, all from within the gentle turns of a wooden maze. 59. Fechner's psychophysics thresholds. In the soft twilight of the 19th century, Gustav Fechner dared to ask a deeply human question: how do we experience the world? As both a physicist and philosopher, he sought to bridge the gap between physical stimuli and our mental perceptions of them. His solution was psychophysics, a new science that quantified the relationship between mind and matter. In a series of delicate experiments, Fechner investigated the thresholds at which we begin to perceive sensations: the faintest sound we can hear, the dimmest light we can see, the softest touch we can feel. His methods involved precise, repetitive tasks in controlled settings, asking participants to detect minimal differences between stimuli. Through this, he formulated mathematical laws showing how sensation grows in relation to stimulus intensity. For example, he found that our perception of light or sound doesn't increase linearly with their physical strength. Instead, perception follows a logarithmic curve, a subtle, scaling sensitivity embedded in our nervous systems. Fechner's work gave science a formal way to measure the invisible, the mind's internal response to the outer world. These insights rippled across psychology and neuroscience, influencing everything from sensory research to user interface design. Even today, when we talk about sensory thresholds or just noticeable differences, we are echoing Fechner's 19th century revelations. In his quiet calculations, he showed that the soul of perception could be mapped in numbers, and that the subjective experience of being alive was, perhaps, not so immeasurable after all. 60. Ramon y Cajal's neuron mapping. Santiago Ramon y Cajal, often called the father of modern neuroscience, peered into the nervous system with the soul of an artist and the mind of a scientist. In the late 19th century, at a time when the nervous system was still believed to be one uninterrupted network, Kajal employed a special staining technique developed by Camillo Golgi. This method allowed individual neurons to be seen in stark contrast against surrounding tissue. What Kajal observed changed the course of brain science forever. Under the flickering light of his microscope, he discovered that the nervous system was made up of distinct, separate cells, neurons, each with its own shape, purpose, and connections. He sketched these intricate structures by hand, producing drawings that are still admired today not only for their scientific importance but for their haunting beauty. His observations led him to propose the neuron doctrine, that neurons are the basic structural and functional units of the nervous system. Kajal's meticulous work laid the foundation for everything we know about the brain's architecture. He saw synapses before they were named, imagined communication between neurons before it was proven, and championed the idea that the brain could change and grow, what we now call neuroplasticity. Long before brain scans and digital imaging, Kajal saw the hidden forest inside our heads and mapped it tree by tree, axon by dendrite. Through his vision, the brain's mysteries began to unravel, one cell at a time. 59. Fechner's psychophysics thresholds. In the mid-1800s, Gustav Fechner sat in silence, staring at a flickering candle, not just as a scientist, but as a man seeking to bridge the chasm between the physical world and the human mind. He believed that every sensation, every sound, sight, or touch, had a quantifiable relationship to the physical stimulus that caused it. To test this idea, he created systematic experiments where he increased sensory stimuli in precise increments and recorded when participants began to detect them. This became the foundation of psychophysics, a science that measures the link between the physical and the psychological. Fechner introduced concepts like the just noticeable difference, JND, the smallest change in stimulus a person can detect. For instance, if you slowly raise the volume of a sound, the JND is the moment your ears notice the difference. Fechner quantified this relationship with mathematical precision, laying the groundwork for perception studies for generations to come. His work helped scientists understand thresholds of awareness, those mysterious boundaries where sensation shifts from silence to sound, from shadow to light. It brought rigor to the subjective experience and gently invited science into the realm of consciousness. As you slowly drift off, think of the faintest whisper in a still room, the softest brush of fabric, the dimmest star on a cloudy night. These are not just moments, they are thresholds. Fechner showed us that perception has a rhythm, a pulse, and we are always dancing just on the edge of it. 60. Ramon Y. Kajal's neuron mapping. In the delicate twilight of a microscope's glow, Santiago Ramon y Cajal saw something no one else had. The soul of the brain written in the form of tiny, branching trees. In the late 19th century, the Spanish scientist began using a special silver nitrate staining technique, developed by Camillo Golgi, that dyed only a few neurons in a brain sample. But unlike others, Kajal saw patterns where most saw chaos. He spent countless hours peering into slices of brain tissue, sketching by hand the intricate structures he saw. These sketches, remarkably beautiful and haunting, revealed neurons as individual, discrete cells, not as a continuous web as was commonly believed. This revolutionary insight formed what we now call the neuron doctrine, the idea that neurons are the fundamental, separate units of the nervous system. Kajal's maps of the brain laid the foundation for modern neuroscience. He described how electrical signals moved in one direction from the dendrites to the axons and proposed the idea of synapses, the tiny gaps between neurons through which information passes. Without him, our understanding of brain function, thought, memory, and emotion would still be wrapped in mystery. As your mind wanders in the quiet moments before sleep, imagine your thoughts flowing like whispers through a forest of neurons, leaping from branch to branch, lighting up entire constellations within your brain. Kajal spent his life unveiling the secret trees in our minds. And now, as you rest, those same trees gently hum with dreams. 61. Titchener's introspection studies. Edward Titchener, an English psychologist working at the turn of the 20th century, believed that the only way to truly understand the mind was to look inward very, very carefully. He built on the ideas of his mentor Wilhelm Wundt, but took the practice of introspection to an extreme level of detail. His students were trained to observe and report the contents of their own consciousness with precision, as if dissecting thought itself. Titchener would present his subjects with simple sensory experiences, a taste, a tone, a flash of light, and ask them to describe everything they experienced in that moment. Not just the sensation, but its intensity, quality, and timing. Was the sound sharp or dull? Was the taste bitter or metallic? And did that feeling trigger an emotion, an image, a memory? Through this method, Titchener hoped to break consciousness down into its most basic elements, like a chemist dividing compounds into atoms. His approach, known as structuralism, sought to map the architecture of the mind. Though later criticized for being too subjective and difficult to verify, Titchener's work was an early attempt to treat the mind scientifically. It helped pave the way for future explorations into cognition, emotion, and perception. As you lie still and reflect, you can almost practice what Titchener taught. Listen to the ticking of a clock. Feel the weight of the blanket. Notice each flicker of thought before it fades. You're not just sleeping, you're exploring the quiet architecture of your own mind. 61. Titchener's introspection studies. In the quiet lecture halls of the late 19th century, Edward B. Titchener invited his students into a world of inner exploration. A firm believer in Wilhelm Wundt's experimental psychology, Titchener brought the method of introspection to English-speaking science. But unlike Wundt, who emphasized objective measurement, Titchener honed in on the subjective, training participants to describe their thoughts and sensory experiences in rich, granular detail. A student might not just say, "I saw a red apple," but instead report, "a round, crimson shape with smooth glossiness and a mild sharpness of scent." Through thousands of these introspective reports, Titchener hoped to map the structure of the mind. He believed that consciousness could be broken down into basic elements, sensations, images, and feelings, much like how a chemist decomposes compounds into atoms. His approach, called structuralism, sought to be the periodic table of mental life. Despite the care taken in training and recording, introspection proved deeply flawed. Reports were inconsistent across individuals, and the method relied heavily on verbal articulation, excluding nonverbal thinkers or those with different internal experiences. Moreover, behaviorism soon eclipsed introspection in popularity by focusing on observable, measurable behaviors. Yet, Titchener's experiments left a lasting legacy. His work underscored the importance of self-awareness in psychological research and ignited questions that modern cognitive science still investigates. How do we experience thought? What is the structure of consciousness? While his method may have faded, his desire to understand the inner life of the human mind never stopped resonating. Tonight, as you close your eyes, imagine yourself in one of those quiet rooms, gently describing your thoughts as they form and dissolve, like ripples across a moonlit lake. The very act of observing your mind, softly and without judgment, connects you to the echoes of those early explorers of the psyche. 62. Ebbinghaus's forgetting curve. In the late 1800s, Hermann Ebbinghaus embarked on a solitary and rigorous journey into the nature of memory. He wasn't content with speculation, he wanted numbers, patterns, and timelines. So, in the quiet hours of his study, Ebbinghaus devised long lists of nonsense syllables, like 14, QF, and ZT, and committed them to memory. With no inherent meaning to these syllables, he ensured his results wouldn't be biased by prior associations. Then, at precise intervals, he tested himself to see how much he remembered. What emerged was the now famous forgetting curve, a steep decline in memory shortly after learning, which then tapers off. In the first hour, retention drops dramatically. Within a day, much is lost. But what remains tends to stabilize over time. Ebbinghaus also discovered that repeated review slows this decline. Spacing out study sessions over days helps memory last. This curve remains a cornerstone of modern learning theory, underpinning educational strategies like spaced repetition and flashcard systems. Yet, the image of Ebbinghaus alone with his syllables carries its own poetic weight. In an age before brain scans and AI tutors, here was a man quietly mapping the ghostly trace of knowledge fading from the mind. As you drift to sleep, think of your thoughts as syllables you once knew but now forget. Like stars at dawn, they vanish, not lost, but hidden. And in that forgetting, in that graceful release, Ebbinghaus found not failure, but rhythm, the pulse of memory, soft and steady, ever renewing itself. 63. Binet and Simon's mental age scaling. At the dawn of the 20th century, French psychologist Alfred Binet, alongside his colleague Theodore Simon, was given a task that would change psychology forever. The French government wanted to identify children in school who needed extra help. But how could one measure something as invisible and complex as intelligence? Binet approached the question not with abstract theory, but with deep empathy and a practical spirit. He and Simon developed a series of simple tests, tasks involving memory, problem-solving, pattern recognition, and language. But their genius lay in how they interpreted the results. Instead of labeling a child simply as smart or not, they introduced the concept of mental age, the level at which a child was functioning intellectually regardless of their actual age. A 7-year-old might perform like a 9-year-old, or vice versa. This helped teachers tailor instruction more effectively and compassionately. Binet firmly opposed using his test to assign permanent labels. He believed intelligence was fluid, influenced by environment and motivation. Sadly, later adaptations like the IQ test would lose this nuance, turning a tool for support into one for judgment. Still, Binet and Simon's original vision was one of care and curiosity. Their quiet revolution in understanding human potential echoes even now in classrooms and clinics around the world. So tonight, as you rest, picture a classroom from 1905, sunlight on wooden desks, curious eyes looking up. Somewhere in that room, a teacher, holding Binet's notes, sees not a number, but a future full of possibility, waiting to unfold gently in its own time. 62. Ebbinghaus's forgetting curve. In the late 19th century, a German psychologist named Hermann Ebbinghaus embarked on an unusual journey. He wanted to measure memory itself. Not just what we remember, but how quickly we forget. At a time when most psychological ideas were speculative, Ebbinghaus turned to rigorous experimentation. He created lists of nonsense syllables, meaningless combinations like DX or BOK, so that prior knowledge wouldn't affect results. Then he memoized them, recited them, and tracked how long he could recall them. What he discovered is now famously known as the forgetting curve. Ebbinghaus found that memory doesn't fade at a steady pace. Instead, we forget most information soon after learning it, and then the rate of forgetting slows down over time. For example, without reinforcement, nearly half of newly learned material could vanish within an hour. But if that same material is reviewed, the curve resets and retention improves. He also introduced the spacing effect, showing that information retained over multiple space sessions is better remembered than when crammed in a single sitting. Though his method seems simple by today's standards, his insights revolutionized education, study techniques, and our understanding of the mind. Schools, memory apps, and learning models still apply Ebbinghaus's findings today. So as you drift into sleep, think about the gentle arc of memory, how it rises with effort and dips with time. Like writing in sand, the marks fade unless we revisit them. But that's okay. Rest allows the mind to consolidate what matters. Sleep itself, Ebbinghaus would be delighted to know, helps protect what we learn. Let your dreams now help stitch today's thoughts into lasting patterns. 63. Binet and Simon's mental age scaling. In early 20th century France, the government sought a way to identify school children who needed special educational assistance. Into this challenge stepped Alfred Binet and his colleague Theodore Simon. Their task was not to judge intelligence broadly, but to understand a child's current learning ability, a radical notion for the time. They created a series of tests that would later become the foundation of the modern intelligence test. These included simple tasks like identifying objects, repeating numbers, defining words, and solving logic puzzles. But their most profound innovation came not from the questions themselves, but from how they interpreted the answers. Binet and Simon introduced the concept of mental age, the age level at which a child performs intellectually regardless of their chronological age. A 7-year-old who could solve problems typical of a 10-year-old, for instance, was said to have a mental age of 10. This simple framework allowed teachers to see development as a spectrum, not a fixed measure. They warned, however, against using this scale as a permanent label. Intelligence, Binet believed, was fluid and could change over time with support and education. Ironically, though, their work would later be adapted into rigid IQ scores by others. Binet and Simon's contribution was not just scientific, but compassionate. They viewed intelligence as something to nurture, not classify. As you ease into rest, consider the grace in their vision, that everyone learns in their own rhythm. Just as dreams don't follow a clock, neither should our minds. Let go of time and drift inward. 64. Messelson-Stall DNA replication test. In 1958, scientists Matthew Messelson and Franklin Stall conducted what is often hailed as the most beautiful experiment in biology. Their goal was to determine how DNA replicates, a mystery at the heart of life itself. At the time, 3 competing theories existed: conservative replication, the entire DNA molecule stays intact while a completely new copy is made; dispersive replication, the DNA is randomly broken and copied in fragments; and semi-conservative replication, each DNA strand serves as a template for a new one. Messelson and Stall set out to discover which model was true. Using a centrifuge and some clever labeling, they grew E. coli bacteria in a medium containing heavy nitrogen, N15, so their DNA would become denser than usual. They then transferred the bacteria into a medium with normal nitrogen, N14, and allowed them to replicate. After 1 generation, they extracted the DNA and spun it in a density gradient. What they found was elegant. The DNA showed a single intermediate band, exactly what the semi-conservative model predicted. Each new DNA molecule consisted of 1 old, heavy, strand and 1 new, light, strand. Subsequent generations confirmed the pattern. This experiment didn't just answer a theoretical question, it illuminated the mechanics of genetic inheritance. Every time a cell divides in your body, it quietly follows this elegant rule. As you drift into sleep, think of your cells working in gentle rhythm, copying, repairing, passing on life's blueprints. The same pattern over and over, perfected by nature's quiet genius. Sleep, too, is a kind of replication, restoring you night after night. 65. Avery's transformation principle in bacteria. In the quiet corridors of microbiology, Oswald Avery and his colleagues conducted an experiment in the early 1940s that would quietly rewrite the story of heredity. Until then, scientists believed that proteins were responsible for passing on genetic traits. DNA, although known, was dismissed as too simple a molecule to carry life's intricate blueprints. But Avery, building on Frederick Griffith's earlier work, focused on the mysterious transforming principle that could transfer traits between bacteria. Avery and his team isolated different components of bacterial cells to determine which one carried this transformative power. Using a series of chemical treatments, they broke down proteins, RNA, and finally DNA in various samples of the heat-killed virulent Streptococcus pneumoniae. When DNA was destroyed, the ability to transform harmless bacteria into deadly ones vanished. This pointed directly to DNA as the genetic material. Despite its monumental implications, Avery's findings were not widely accepted at first. The scientific community hesitated, clinging to the idea that proteins, with their structural complexity, must be the carriers of heredity. But the seed had been planted. This humble experiment quietly laid the foundation for modern genetics. Without Avery's persistence, Watson and Crick's later discovery of DNA's structure might have never found solid ground. Today, Avery's experiment is a gentle reminder that even the smallest, quietest studies can shake the foundations of science. In the silent shifting of bacterial genes, the entire world of genetics began to blossom, like a whisper that changed the future forever. 66. Spemann's embryonic organizer experiment. At the dawn of the 20th century, when embryology was still wrapped in mystery, German scientist Hans Spemann performed a series of experiments that would illuminate one of the most magical aspects of early development. In his most famous study, conducted with Hilda Mangold in the 1920s, Spemann uncovered what he called the organizer, a region of cells in a developing embryo capable of guiding the formation of entire body structures. Working with frog embryos, Spemann and Mangold transplanted a small section of the dorsal lip of the blastopore, a structure in early development, from one embryo to another. What followed was astonishing. The recipient embryo developed a second body axis, forming twin spines, heads, and nervous systems. This demonstrated that the transplanted tissue held the power to organize surrounding cells, instructing them to form complex structures. This experiment unveiled that certain cells in early embryos serve as a sort of biological conductor, orchestrating the symphony of development. The concept of induction, where one group of cells influences the fate of another, became a cornerstone of developmental biology. Though the experiment required delicate hands and patient observation, its implications were profound. Spemann's discovery of the organizer laid the groundwork for modern stem cell research and regenerative medicine. It showed that identity and fate within living cells are not static, but dynamic, and can be reshaped by their neighbors. As you drift to sleep, imagine tiny frog cells whispering instructions to one another, building life from the simplest beginnings, guided by nature's invisible hand. 67. Morgan's fruit fly inheritance work. In a small, crowded lab at Columbia University in the early 1900s, Thomas Hunt Morgan turned the humble fruit fly into a revolutionary tool for understanding heredity. Working with Drosophila melanogaster, Morgan and his students discovered how traits were passed through chromosomes, forever changing our understanding of genetics. Morgan noticed something peculiar. In a population of fruit flies, a white-eyed male occasionally appeared. By carefully breeding these flies, he observed that this white-eyed trait only showed up in males and was inherited in a distinct pattern. From this, Morgan concluded that the gene for eye color must reside on the X chromosome. This was the first solid evidence that specific genes are located on specific chromosomes. His meticulous work mapping traits in fruit flies eventually led to the first chromosome maps, tracing the location of various genes along the chromosomes. This provided concrete proof that chromosomes were the carriers of genetic material, validating and expanding upon the theories initiated by Gregor Mendel decades earlier. Morgan's lab became known as the Fly Room, a place where monumental discoveries emerged from seemingly insignificant insects. His work earned him a Nobel Prize in 1933 and established Drosophila as a model organism still used in genetics today. As you rest tonight, imagine tiny fruit flies fluttering about under microscopes, carrying secrets that unravel the mysteries of life itself. From their delicate wings emerged truths that shaped the very science of heredity, proving that even the smallest lives can carry the greatest revelations. 68. Vesalius's human dissection corrections. In the hushed chambers of 16th-century anatomy theatres, a young Flemish physician named Andreas Vesalius began to question centuries of unquestioned wisdom. For generations, European medicine had relied on the writings of Galen, a Roman physician whose knowledge of human anatomy came from dissecting animals, not people. But Vesalius had something Galen never did: access to the human body. In 1543, Vesalius published De Humani Corporis Fabrica, on the fabric of the human body, a stunningly detailed anatomical text based on his direct dissections of human cadavers. His work corrected dozens of Galenic errors, such as the idea that the human jaw had two bones or that blood flowed through invisible pores in the heart. With boldness and precision, Vesalius drew the human form as it truly was, bone by bone, muscle by muscle. His book, filled with intricate illustrations, wasn't just a scientific triumph, it was a revolution in how the body was seen and understood. Vesalius challenged authority by insisting that medical knowledge must come from observation, not dogma. Imagine the flickering torchlight in a stone amphitheater, the scent of herbs masking decay, and Vesalius calmly peeling back centuries of misunderstanding with each careful incision. His hands, guided by curiosity and courage, revealed the body as it had never been seen before. As you settle into rest, think of the quiet awe that comes from seeing truth laid bare. Vesalius's courage reminds us that even the most accepted ideas must sometimes be cut open and re-examined. 69. Bray's Naked Eye Astronomical Logs. Before telescopes pierced the skies, a Danish nobleman named Tycho Brahe sat beneath the stars with nothing but his eyes, patience, and handmade instruments. In the late 16th century, Brahe built the most advanced observatory of his era, Uraniborg, where he tracked celestial bodies with unprecedented precision, all without a telescope. Over decades, Brahe recorded the positions of stars and planets night after night, logging their movements with exactness that would astonish even modern astronomers. He noted details down to the arcminute, measuring Mars's wandering path and the sudden appearance of a supernova in 1572, a new star that contradicted the prevailing idea that the heavens were unchanging. What made Brahe's work so influential wasn't just his data, but his relentless devotion to observation. He bridged the mystical skies of medieval astronomy and the empirical age to come. Though he clung to his own hybrid model of the cosmos, a mix of geocentric and heliocentric theories, his meticulous records would become the foundation upon which Johannes Kepler built his laws of planetary motion. Picture Brahe on a chilly Scandinavian night, his brass instruments gleaming under starlight, scribbling notes by candlelight as the constellations wheel slowly overhead. In his dedication, there is serenity, a reminder that great truths often come not from brilliant leaps, but from steady eyes and quiet persistence. As you slip into dreams, imagine stars slowly drifting through Brahe's sky, measured not by machines but by the patient heart of a man who dared to watch. 70. Kepler's elliptical orbit calculations. With Tycho Brahe's astronomical data in hand, Johannes Kepler set out in the early 1600s to solve the riddle of planetary motion. He sought to find harmony in the heavens, expecting orbits to form perfect circles, as long believed. But after years of laboring over the numbers, Kepler made a groundbreaking discovery: the planets don't move in circles, but in ellipses. This realization shattered centuries of belief and launched celestial mechanics into the modern age. Kepler's first law of planetary motion declared that each planet moves in an elliptical orbit with the Sun at one focus. His second and third laws followed, describing the speed of planetary motion and the relationship between a planet's distance and its orbital period. Kepler didn't merely rely on conjecture, he painstakingly aligned theory with observation, guided by Brahe's rich datasets. It was a triumph of math, logic, and humility before nature. Imagine Kepler hunched over pages of calculations, quill in hand, stars spinning above, and the whisper of insight gently nudging him from flawed circles to elegant ellipses. He gave the cosmos a new shape, and in doing so, brought us one step closer to understanding our place in it. As you drift into rest, imagine the planetary dance continuing overhead, not in stiff circles, but graceful ellipses, each motion governed by Kepler's quiet genius. A reminder that sometimes, true harmony comes not from perfection, but from embracing the natural curves of the universe. 71. Schrödinger's thought experiment of the cat. In the strange world of quantum mechanics, Erwin Schrödinger offered one of the most iconic and perplexing illustrations: the thought experiment of Schrödinger's cat. Unlike a traditional experiment conducted in a lab, this one lived entirely in the realm of imagination, and it changed the way people thought about physics and reality. Picture a cat placed inside a sealed box with a small amount of radioactive material, a Geiger counter, and a vial of poison. If an atom of the radioactive material decayed, the counter would trigger a hammer to break the vial, releasing the poison and killing the cat. If the atom did not decay, the cat would live. According to quantum theory, until the box is opened, the cat exists in a strange, dual state, both alive and dead at the same time. Schrödinger wasn't suggesting anyone should do this experiment in real life. Instead, he was illustrating a problem with the interpretation of quantum mechanics. The idea that particles can exist in multiple states until measured was well accepted, but applying that logic to a living creature exposed the weirdness of the theory. It forced scientists and philosophers alike to rethink the nature of observation, measurement, and reality itself. As you lie back and drift off, imagine the sealed box resting quietly, the cat inside curled in a slumber of possibility, neither gone nor fully here. A paradox nestled gently in the folds of quantum uncertainty. In that silence, Schrödinger's cat continues to dream, both waking and sleeping in a universe where observation shapes truth. 72. Heisenberg's uncertainty principle in action. Werner Heisenberg's uncertainty principle is one of the cornerstones of quantum mechanics. Formulated in the 1920s, this principle fundamentally challenged the way we observe and understand the microscopic world. It tells us that certain pairs of physical properties, like a particle's position and its momentum, cannot both be precisely known at the same time. The more accurately we know one, the less accurately we know the other. Heisenberg came to this realization through the mathematics of wave-particle duality. In attempting to measure subatomic particles like electrons, scientists found that observation itself disturbed the particles. Imagine shining a light to see an electron. The very act of shining that light moves it. This means there's a limit to what can be known, not because of faulty tools, but because of nature's built-in uncertainty. This wasn't just a philosophical puzzle. It had real consequences. It revealed that at the most fundamental level, nature is probabilistic, not deterministic. It laid the groundwork for quantum theory, influencing everything from particle physics to the development of quantum computing. As you settle into sleep, imagine an electron quietly humming along its wave path, its location blurred, its speed a mystery. It dances just out of reach, a soft whisper in the quantum dark. Heisenberg's principle reminds us that not everything must be known to be real, and that even uncertainty has its beauty, like a mist drifting through the night. 73. Planck's blackbody radiation studies. At the dawn of the 20th century, physicist Max Planck faced a stubborn problem: the behavior of radiation emitted by heated objects. What scientists called blackbody radiation couldn't be explained by classical physics. When plotting the intensity of emitted light across wavelengths, the math suggested something absurd: energy output would become infinite at shorter wavelengths. This divergence became known as the ultraviolet catastrophe. To fix this, Planck made a bold assumption. He proposed that energy isn't emitted continuously, but in discrete packets or quanta. It was a radical idea at the time, and one he initially viewed as a mathematical trick. But the math worked. His quantum hypothesis fit the experimental data perfectly and opened the door to quantum mechanics. Planck's constant, a fundamental number that relates the energy of a photon to its frequency, emerged from this work. This simple constant bridged the world of the very small with universal laws. Planck's insight soon inspired others, like Einstein, who used the quantum idea to explain the photoelectric effect. As you close your eyes, imagine glowing embers in a fire, radiating warmth and light in waves. Now zoom inward, to the invisible quantum leaps powering that glow. Planck's work revealed that even firelight carries a story of cosmic order, measured in the tiniest flickers of energy. In every spark, the beginning of quantum physics burns quietly, illuminating the invisible with each gentle quantum step. 74. Foucault's pendulum and Earth's rotation. In 1851, Léon Foucault revealed Earth's quiet dance through a beautifully simple experiment: a swinging pendulum. Deep in the Pantheon of Paris, he suspended a heavy iron ball from a long wire, letting it swing freely over a circular platform. What seemed like a simple motion held a deeper truth. Over time, the path of the pendulum appeared to rotate, tracing out a slow spiral. But it wasn't the pendulum that was moving, it was the Earth beneath it. This mesmerizing demonstration provided direct, physical proof that the Earth rotates on its axis. Until then, such rotation had been inferred mathematically or indirectly. But Foucault's pendulum made the invisible motion of our planet something one could actually see, slowly ticking against the backdrop of the cosmos. The experiment depends on inertia. The pendulum maintains its swing in the same plane while the Earth rotates beneath it. At the poles, the rotation would be complete every 24 hours. At the equator, it would show no rotation. In Paris, the shift was gradual but clear. Imagine standing beneath that massive pendulum, the hush of the Pantheon around you. The slow, steady sweep of the pendulum whispers of celestial motion. It's a gentle reminder, we are always moving, even when we feel still. As you rest tonight, think of that quiet swing in a shadowed dome, marking time not with ticks and tacks, but with the turning of the Earth itself. A lullaby written by gravity and the stars. 75. Marconi's long-distance radio wave test. In the dawn of the 20th century, Guglielmo Marconi stretched the boundaries of human connection, not through wires or pipes, but through the air itself. In 1901, he conducted one of the most significant experiments in communication history by transmitting a wireless signal across the Atlantic Ocean. From Poldhu in Cornwall, England, to Signal Hill in Newfoundland, Canada, Marconi sent the letter S in Morse code, a simple sound that echoed across 2,000 miles of open sea. This experiment was bold, even outrageous for its time. Many doubted it could succeed. Scientists believed the Earth's curvature would block such long-distance waves. But Marconi, with intuition and perseverance, proved them wrong. He capitalized on atmospheric reflection, unknowingly using the ionosphere to bounce signals over the horizon. Marconi's success didn't just revolutionize communication, it opened the door to the modern wireless world: radio, television, satellite signals, and Wi-Fi. He made distance disappear, uniting voices and ideas across continents. His accomplishment showed that invisible forces could connect us, that unseen waves could carry meaning and intent. Picture the quiet crackle of a signal leaping from one lonely station to another over vast waters, a whisper reaching from one end of the world to the other. A bridge not built with stone, but with resonance. As you close your eyes, imagine that first faint S drifting through the sky, a soft ripple in the invisible fabric between us. A symbol that connection, no matter the distance, is always possible.